Hello, class. Continuing on the lecture for Laws of Sine, section 3.5. We did the two angles and one side, and now we're going to do what the book calls the ambiguous case. But basically, the idea on this triangle is that if you have two sides and an angle that's opposite to one of those sides, you can also use the laws of sines. And so let me show you a couple PowerPointers here, PowerPoint slides. And like I said, they call this the ambiguous case. So this is the idea where you have two sides and an angle where this angle is opposite. And so what do we mean by that? Well, let me pull up the whiteboard real quick and show you what we mean. And so this is the example we're going to do first. So let me just draw this here. So you remember we had these three, right? And so this was B, this was C, this was A. So this was angle A. I'll just use capital A. And this was capital B. And this was capital C. So those are the angles. So say like we have 42 degrees and we have B equals 12 feet and we have A equals 22 feet. So you could see if you have these opposites here, right? You see what we mean by opposite? 42 angle A is opposite to that side A. So if we had C and B, that would be adjacent, right? Angle A is adjacent to B and C. So this is the opposite. So again, we would use laws of sines. And we're going to do that problem in a minute, or maybe two. But getting back to the PowerPoint, it's really kind of crazy that depending on the type of triangle, you could have a variety of different solutions. And what we mean by that is, to me, here is the matrix. And you could see that the height is B sine of A, which back in the day before you knew trig, that was the only way you could calculate the area, right? You needed the height of the triangle. So in this case, this is, but you see they talk about H and B. Well, the ambiguous condition is this fourth column here, where there's two possible solutions. And that only occurs when A is less than B. So there is two solutions or there are no solutions. All the other ones are kind of nice, right? You could have no solutions, but you would just walk through that. But you could see this is a right triangle. And then when A is greater than B, you always have one solution, which is actually quite nice. So what we're going to start with is the one solution approach. And so the way to strategize this, and why won't the whiteboard come up? Okay, so the way to strategize this is that you see that we have the opposite. So we're going to use laws of sines. And you could see that the A value, right, is greater than the B. So we don't have that crazy ambiguous state. It's only when A would be less than with regard to that. And remember, we're using A and B. You want to think about this as the opposite is the A value and the adjacent is the B value, right? From our sines and cosines idea with regards to that. And so we'll walk through an ambiguous situation, but let's start with this one, which is not. And so this one, since the opposite is greater than the adjacent, we do not have an ambiguity. The only time you have an ambiguity is when the opposite would be less than the adjacent. And so in this case, we don't, where A is opposite and B is adjacent. So let's walk through this again. Remember, sine of A over A, sine of B over little b equals sine of C over little c. Okay, so you walk through this and we have three values. So we want to use A, right? So this would be sine of A over A. And then we have one value, which is little b, right? Over little b. So let's plug these in and see what we get. So if you did that, you would plug it in, you'd get sine of 42 divided by 22 equals sine of b, right? We want to calculate b over little b, which is 12. So you do a little algebra, and you end up with sine of our angle b equals 12 times sine of 42, all divided by 22. So if you did this and plugged it into your calculator, if I did it right, you would get 0.365. So how we find angle B? Here we do the sine inverse, right? So angle B would be sine inverse of 0.365. And so if you get out your calculator, and again, this would be in the first quadrant, I got 21.4 degrees. Okay, so just gonna try to get a different color here. Let's use blue. So what's that? Angle B, so that's 21.4 degrees. Okay, so now we have two angles. Go back to the old, add everything up, right? So let's do that first to find the third angle. So once you have two angles, you don't have to get at your trig thing, right? We just add them all up. So angle C would be 180 minus 42, which is angle A, minus 21.4, which is angle B. And if you did that, we get 116.6. So this would be 116.6 degrees. So then what do we do for the last one? Well, what do we do for the last one is this. So you could pick anything here. I might as well use A since we used it before, right? So it'd be sine of A over little a equals sine of C over little c. And when you plug those in, you get sine of 42 over 22 equals sine of, what was that, 116.6, which is C, divided by little c. So you set that up and you would get, let's see here, you'd get 22 times sine of 116.6, all divided by sine of 42. You plug that into your calculator and you would get 21.4 feet. So this one here would be 29.4 feet. So the strategy typically is given two sides and the opposite angle is find the angle of the other opposite side first, which was typically, in this case, was our B. And then once you have that, use the triangle rule of 180 degrees to find the missing third angle, which was our C angle. And then at the end, you kind of do what we did in the first example, calculate the last missing side using the laws of sines again. So that's the strategy. So the next example we're going to do is a application one. And then I'm going to stop the lecture and then do the ambiguous case in its own lecture because it's going to take a while. So this one's kind of a fun one. So let me show you this one. I'll clear this out of here. So how about if we had a problem like this, which is kind of fun. And so here it says a satellite orbiting the Earth directly overhead at observation stations in both Phoenix and Los Angeles, which are 340 miles apart. And so at the instant when the satellite is between the two, its angle of elevation is observed simultaneously at 60 degrees and 75 degrees. How far is the satellite from LA? Or you could ask how far the satellite is from Phoenix. Very similar calculation. Here is the law of sines work with. right? We have two angles, boom, boom, and we have the distance between the two cities. So I'm going to use the PowerPoint because it has prettier slides here. But you can see if the satellite's up here, right? You can see the distance from LA to Phoenix is 340. So again, you have to label these. And it doesn't matter where A, B, and C is. But remember, angle A is always opposite of side A. Angle B is always opposite of side B. And angle C is always opposite of side C. So we labeled this one up here as C because the opposite is the distance between Phoenix and Los Angeles. So it's easy to find angle C, right? 180 minus 75 minus 60, so that's 45 degrees. So what we're worried about is which one? Well, the problem asked, how far is the distance from the satellite to Los Angeles? So if you look at our triangle here, it's little b, right? That's what we want to calculate. So here's why we end up using this calculation, because we know C, now we know angle C, and we know angle B, that's given to us by 60 degrees, and so we find little b. So again, I'll leave that to you to plug in those numbers, but you see very similar calculation and plug everything in there. You could see it's about 416 miles from that satellite to the ground of Los Angeles where that observation station is. Okay, so that'll end the lecture, second lecture, law and signs. I'm going to do one more, which does the ambiguous case.